So in this lecture, I will discuss series of random variables. So the theorem which we will prove in this lecture is the following. Consider a sequence x1, x2 of independent random variables. Denote by Sn the sum of the first n random variables. Then I claim that if Sn converge in distribution, so if the distribution measure of the random variable Sn converge weakly to some measure mu, then Sn converge in probability, which means that there exists a random variable S such that Sn converge to S in probability. And of course, the distribution of S, so the distribution measure of S coincides with mu, which is the weak limit of the sequence mu Sn, which means that if Sn converge in distribution, then actually it converges in probability. Of course, you know already that if Sn converge in probability, then it converges in distribution. This is already known, but what's new here is that we will prove that convergence in distribution implies convergence in probability. So that's the first statement. And the second statement will be, well, if Sn converge to S in probability, then it converges almost surely. So again, if Sn, you know already that if Sn converge to S almost surely, then it converges in probability. But here we will prove that if it converges in probability, it converges almost surely. Which means, if you put together 1 and 2, that in order to prove that a sequence as a series of independent random variables converge almost surely, it's enough to show that it converges weakly. The proof of this theorem relies on two lemmas. So let me state the first lemma. So lemma 1 states the following. Assume that you have a sequence xn of random variables which are Cauchy in probability. And I will state exactly what Cauchy in probability means. Then I claim there exists a random variable x such that xn converges to x in probability. So let me explain what Cauchy in probability means. Well, it means that for all epsilon positive, so this is Cauchy in probability, for all epsilon positive, the limit as n and m converge to plus infinity of the probability that xn minus xm larger than epsilon, that this is 0. And what does it mean that the limit of n and m converge to plus infinity? It means that for all delta, I can find n0 such that if n and m are larger than n0, then this probability of xn minus xm larger than epsilon, that this is less than delta. So what I'm saying that this sequence is Cauchy in probability, it means that for all epsilon and for all delta, I can find n0 such that if n and m are larger than n0, then this probability is bounded by delta. So what I claim is that, well, if a sequence xn satisfies this assumption, then I can find a random variable x, and I can show that xn converge in probability to this random variable. So I rewrote here the assumption, and there the thesis. So the proof is divided in two steps. In the first step, I want to construct this random variable x. So let's take epsilon equal to 1 divided by 2 to the power k. And by assumption, I know that the limit as n and m goes to infinity of the probability that xn minus xm larger than 1 over 2k, then this is 0. This means that I can find nk such that this probability is larger than 1 over 2 to the power k if n and m are larger than nk. So there exists this nk such that if n and m are larger than nk, then this probability xn minus xm is larger than 1 over 2k, that this is bounded by 1 over 2k. So I can, of course, assume that nk is an increasing sequence, that nk is strictly smaller than nk plus 1. Because, well, if nk plus 1 it's not smaller than nk, we can just define nk plus 1 as nk plus 1 to get a new sequence which is increasing. So I'll be assuming that this sequence it's increasing, and since this sequence is increasing, I have that this inequality holds for m equal to nk and n equal to nk plus 1. So what I know is that the probability that x nk plus 1 minus x nk, this is larger than 1 over 2k, it's bounded by 1 over 2k. Now, well, it follows from this that what is the probability that there exists a j larger than k such that x nj plus 1 minus x nj, that this is larger than 1 to the power 2j. Well, this probability, of course, the probability of the union, it's bounded by the sum. And, well, the probability of each event, it's bounded by this quantity. So this is bounded by 1 over 2j, and this is equal to 2 divided by 2k. So we have a bound for this event, the union of these sets. This is bounded by 2 divided by 2 to the power k, and this means that the probability, if now I take the intersection, so this is as k increase, we are taking union over less and less sets. So this is a decreasing sequence in k, and this sequence is decreasing to the intersection for k larger than 1 of the union of j larger than k of this event, x nj plus 1 minus x nj larger than 1 over 2j. And, well, this is a sequence which is decreasing to this one, and therefore the probability of this event is equal to the limit of this probability as k tends to plus infinity, and this is 0. So I will define the set A to be the complement of this set. So let A be the set which is the complement of this one, which is the union over k, the intersection of j larger than k of the set that x nj plus 1 minus x nj, that this is bound by 1 over 2j. And it follows from this identity that the complement has probability 0, which means that the probability of A is equal to 1. And now, well, let's consider an omega which belongs to A. And what I claim is that for omega in this set, then the sequence x and j of omega converge. So let's consider omega in A. And what I claim is that if omega belongs to A, then x n of omega converge to some limit, which I will call x of omega. And this is clear because the sequence x and j of omega is Cauchy. So what I claim is that if you take an element of this set in this set A, the sequence x and j omega, it's a Cauchy sequence in J. And well, and this is clear because if you consider a j smaller than k, then x and k of omega minus x and j of omega, you can rewrite this difference as a telescopic sum. So this is equal from I from j is the smallest one to k minus 1 of xn I plus 1 of omega minus xn I of omega. And this is bounded by the sum of the absolute values. And each, well, since omega belongs to the set A, you know that x and I plus 1 minus x and I is bounded by 1 over 2a, 2 to the power I. And this is bounded by 2 divided, so this is j, 2 divided by 2 to the power j. So if j is sufficiently large, this difference it's bounded by epsilon, whatever k, and therefore this sequence, the sequence x and k omega, it's indeed Cauchy. Right? If you fix an epsilon, now you choose j for this number to be smaller than epsilon, and therefore for all j and k, or for all I and k larger than this j you obtained, this difference will be bounded by epsilon, and therefore this sequence is a Cauchy sequence. Now we know that a Cauchy sequence of real numbers it's convergent, so you know that indeed there exists a limit, and I will represent this limit by x of omega. So what we get from here is that for all omega, the sequence x and j of omega converge to x of omega, and therefore this sequence it's converging on the set A. The set A has probability 1, so this means that this sequence x and j it's converging almost surely to this random variable x, and in particular, well, x and j it's converging in probability to this random variable x. So up to now, I constructed in this probability space a random variable x, and we know that the sequence x and j it's converging to x in probability. So this completes step 1 of the proof, and now I'll go to the step 2, which consists in showing that actually the sequence xn it's converging in probability to x. So not only x and j, but actually the whole sequence it's converging to this random variable x. So in the first step, we constructed a random variable x and a subsequence nj such that x and j converge to x in probability. Now we want to prove that xn converge to x in probability. To prove that xn converge to x in probability, fix an epsilon positive, and what we need to show is that the limit as n goes to infinity of the probability that xn minus x it's larger than epsilon, that this is equal to 0. So fix now a delta positive, and we need to show that the probability of xn minus x larger than epsilon, that this is bounded by delta. Right, so epsilon and delta are fixed, and now let me use the assumptions. On the one hand, I know that this limit, that the sequence is Cauchy in probability, so I know that there exists n0 such that if n and m are larger than n0, then the probability that xn minus xm it's smaller than epsilon divided by 2, that this is bounded by delta. So this comes from the assumption. On the other hand, I know also that xnj is converging to x in probability. So this means that there exists a j0 such that if j is larger than j0, then the probability that x and j minus x larger than epsilon over 2, that this is bounded by delta. So now let's take here, so there exists this n0 and there exists this j0. So let me take n, which is larger than n0 and larger than nj0. So n0 is given by the assumption, j0 is given by the first part of the proof, and so to it, it's associated nj0. So let me take n, which is larger than n0 and nj0, and let me take a j. Now I fix a j larger than j0. And what I want to divide it, say that, well, this probability, it's bounded by the probability that xn minus x and j larger than epsilon divided by 2 plus probability that x and j minus x larger than epsilon divided by 2. Right? So if this probability is larger than epsilon, then either this one is larger than epsilon over 2 or this one is larger than epsilon over 2. And what is j here? Well, I will choose a j which is larger than j0 and such that nj is larger than n0. So n0 is fixed, it's given by the assumption of the theorem, and j0 is fixed, it's given by the first part of the proof. And now I just choose one j which is larger than j0 and such that nj is larger than n0. And for that nj, well, if I look at the first term, nj is larger than n0. I take n larger than n0. This means that both n and nj are larger than n0, which means that by the assumption, this first term is bounded by delta. Now for the second one, well, since j is larger than j0, x and j minus x by the first part of the proof, it's bounded by delta. And therefore, the sum is bounded by 2 delta, and this shows that indeed, for all n larger than n0, this probability is bounded not by delta, but by 2 delta, but this is the same, and therefore, that this limit is equal to 0, and that proves that indeed the sequence xn is converging to x in probability, and this completes the proof of the first lemma. So the second lemma can be stated as follows. So you consider again a sequence of random variables xn, and now you assume that the probability that the maximum between m and n of xk minus xn larger than epsilon, so that for all epsilon, this quantity tends to 0 as m and n tend to plus infinity. So that the limit as m and n tend to plus infinity of this quantity, it's equal to 0 for all epsilon positive. So here again, what it means that, well, whatever epsilon you fixed and whatever delta, you can find n0 such that if m and n are larger than n0, then these probabilities are bounded by delta. So you see that the hypothesis is similar to lemma 1, but now we have a stronger condition, a stronger hypothesis, because we have a maximum inside. And what I claim is that under this assumption, there exists a random variable x, and such that xn converge to x almost surely. So what we will do, which is also similar to the previous lemma, is that we will construct a set which has probability 1, and we will show in this set that there exists a random variable defined over there, and that xn converge to x in this set. So let's start the proof. The beginning of the proof is similar to the proof of the previous lemma. So you fix epsilon equal to the power 1 to the power 2p. You fix an integer p. You take epsilon equal to 1 over 2p in these hypotheses. So you know that this limit is equal to 0. So if you fix delta equal to 1 over 2p, what you get is that there exists an integer np, such that if n is larger than m, and this is larger or equal than np, then the probability that the maximum of k between k and n of xk minus xm, I'm sorry, here it's m. So we are comparing k to the first term. So I'm sorry, here it's m is the first term of this interval. So xk minus xm, larger, we took epsilon equal to 1 over 2p, so that this is bounded by 1 over 2p. So again, I fixed epsilon equal to 1 over 2p, delta also equal to 1 over 2p, and by assumption, we can find np such that if n and m are larger than np, then the probability of this event is bounded by 1 over 2p. Now, if I take, of course, the union of these sets, so if I consider, I fix q, and I take the union for p, okay. Before I do that, let me just remind you that I can always assume that this sequence np, it's increasing. Okay, so I'm assuming here that np plus 1, it's larger than np. And this is always possible because if np plus 1 it's less or equal than np, I can just change the definition of np plus 1 to guarantee that this inequality holds. So once you accepted that np plus 1, np it's an increasing sequence, well, let me take in this probability m to be np and n to be np plus 1. So it follows from this inequality by taking m equal to np that the maximum for k between np and np plus 1, that xk minus xnp larger than 1 over 2p, that this is bounded by 1 over 2p. Right? Since this is true for all n and m larger than np, I can take m equal to np, n equal to np plus 1 to get this bound. And now, as I was saying, you fix an integer q, and let me take the probability of the union. So what I want to do is consider the union for all p larger than q of this event, so that the maximum for k between np and np plus 1, that xk minus xnp larger than 1 over 2p. Well, the probability of this union, it's bounded by the sum of these probabilities. So by summing 1 over 2p for p larger than q, what I get is that this is bounded by 2 divided by 2 to the power q. And, well, I'm almost done, because if I call this set here the set BQ, you see that when I take Q plus 1 instead of Q, I'm doing the union over a smaller quantity of sets. And this means that the sets BQ are decreasing. Okay, so this means that BQ contains BQ plus 1. And therefore, this means that the sets BQ are decreasing to the intersection of all Q's. So Q prime for Q prime larger than 1. And in particular, the probability of BQ, which is this set, it's converging to the probability of the intersection. So let me write it quickly here. So since BQs are converging to this intersection, the probability of the intersection for Q larger than 1 for P larger than Q of the maximum of NP less than K less than NP plus 1 of xk minus x and p to be larger than 1 over 2p. So the probability of this event, it's equal to the limit in Q as Q tends to infinity of these probabilities, but this is equal to 0. So the probability of this set, it's equal to 0, and I will call this set A complement. So A has probability 1. And what is A? Well, A, so I'm calling this intersection A complement. Since A complement has probability 0, this means that the probability of A, it's equal to 1. And what is A? A, it's equal to the union for K larger than 1 of the intersection for P larger than Q, that the maximum for K between NP and NP plus 1, that xk minus x NP, that this is bounded by 1 over 2p. So here is the definition of my set A, and I know that the probability of A is equal to 1. Now at this point, I will concentrate on this set, and I will show that in this set, xn, there exists a random variable x, and xk, it's converging to x in this set, which has probability 1. That will prove, that will show that xk converges to x almost surely. So up to this point, I constructed a set A. So the set A is defined here again. To construct the set A, actually, I just defined the sequence NP. And once this sequence NP is defined, I define A by this identity. And what we proved is that the probability of A is equal to 1. Now, I will fix an element omega in A. And I want to prove that there exists a random variable x of omega such that xn of omega converge to x of omega for these omegas. So this is what we will do next. So we have first to define what is the random variable x, and then show that xn converge to x. Now fix omega in A. Since omega belongs to A, it belongs to this union. So that means that there exists a Q0, which depends on this omega, such that omega belongs to the intersection, to this intersection, to P larger or equal than Q0 of the maximum. For NP smaller than K, less or equal than NP plus 1 of xk minus xnp less than 1 over 2p. Right, so we have seen, well, omega belongs to this set. Now, since omega belongs to this set, this means that if I take here k to be np plus 1, this means that x np plus 1 minus x np at omega, it's bounded by 1 divided by 2 epsilon. So this means that for all p larger than this q naught, we have that x np plus 1 of omega minus x np of omega, that this is bounded by 1 over 2 epsilon. And so what I claim now is that this sequence x np of omega is Cauchy. And I won't write again of omega. I'll just write it as x and p, and it's meant that it's x and p computed at omega. So I claim that this sequence x and p, it's Cauchy. So to prove that it's Cauchy, you fix an epsilon positive, and you have to find a p naught such that, well, so let me fix first a p1, which is such that 1 over 2 divided by 2 p1, it's less or equal than epsilon. So you fixed an epsilon. Now you find a p1 for which 2 divided by 2 p1, it's less than epsilon. And now you choose p2 as the maximum between q naught and p1. So p2 is this maximum, so p2 it's larger than q naught. So I know that this is true for p larger than p2, and I know also that 2 divided by 2 p2, it's bounded by epsilon. And so let me erase the definition of A, and let me show that x and p, it's indeed Cauchy. So for that, let me fix p larger than r and larger than what I called p2. And let me compare x and p and x and r. Remember that here I'm computing at omega, but I'm not writing omega anymore, just to keep notation simple. So I can write this difference as a telescopic sum and bound it by the sum for k going from r to p minus 1 of x and k plus n k plus 1 minus x and k. Now, since k is larger than r and r is larger than p2, so, and p2 is larger than q naught, so I know that this inequality holds for k. So this is bounded by k from r to p minus 1, 1 over 2k, and this is bounded by 2 times divided by 2 to the power r, and here, since r is larger than p2 and p2 is larger than 1, I have that this is bounded by epsilon. So indeed, for a fixed epsilon, I constructed a p2 such that if p and r are larger than p2, x and p minus x and r, it's bounded by epsilon, and this means that indeed the sequence x and p, it's Cauchy. So this is the first step. Now I will erase everything. I'll just remind you that x and p is Cauchy, and that I'm fixing omega in this set to prove now that xn converge to x. So we constructed a set A, which has probability 1, and we've seen that if omega belongs to A, it belongs to this set for a certain q naught. And we proved also that for omega in A, x and p naught, it's Cauchy. It's a Cauchy sequence. Well, since it's a Cauchy sequence of real number, this means that it converges, and I will represent by x of omega the limit. So x and p of omega, it's converging to some limit, and this limit I'm representing by x of omega. X, of course, it's measurable because, well, it's the limit of a sequence of measurable functions, which means that x is a random variable. It's measurable. That means that x is a random variable. Now what remains to be done is to show that xn of omega converge to x of omega. So this is what I want to prove. Now to complete the proof, remember that we want to show that xn converge to x almost surely. So to prove that, you fix again an epsilon positive. Now first, I still need to consider Q0. Then let me introduce P1, which is, well, I know that x and p is converging to x0. So there exists a P1 such that if p is larger or equal than P1, x and p of omega minus x of omega, that this is bounded by epsilon. So the existence of P1s comes from the fact that x and p is converging to x0. And now I'm getting a P2, and P2 is such that 1 over 2 divided by P2, it's bounded by epsilon. So this is also clear that it exists, so this is not a power, it's an index. There exists a P2 such that 1 over 2 to the power P2, it's bounded by epsilon. And let me take now, I don't know, P0 to be the maximum between all these quantities. So P0 will be the maximum between Q0, P1, P2. And finally, let's consider n, which is larger than n P0. So here is n P0 at some point, and I'm taking n larger than this quantity, so n is somewhere here. And of course, n is contained in an interval which is, I need a name for that, nr. So this is nr, and this is nr plus 1. And n is strictly larger than nr, and less or equal than nr plus 1. And of course, for that, I know since n is larger than np, this means that r is larger than p0. Now I want to estimate xn of omega minus x of omega. I claim that this is bounded by 2 epsilon. And the way in which we show that is that, well, I will compare xn to xnr and xnr to x. So this is bounded by xn of omega minus xnr of omega plus xnr of omega minus x of omega. Now you see, since n it's contained, it's larger than nr and smaller than nr plus 1, this is bound, the first term, it's bounded by the maximum for k between nr and nr plus 1 of xk minus x and r. And, well, since r it's larger, I wrote that somewhere, since r is larger than p0, and p0 it's larger than p2, this, well, we are also larger than q0, so we know that omega belongs to this set. So we know that this maximum, it's bounded. So let me write it in. So this maximum, it's bounded by 1 divided by 2r. This comes from the fact that omega belongs to this set, and r, it's larger than q0. So since r it's larger than q0, omega belongs to this set for p equal to r, and therefore this maximum, it's bounded by 1 over 2r. Now, since r it's larger than p2, well, r it's larger than p0, and p0 is larger than p2, we have that 1 over 2r, it's bounded by epsilon. So this quantity here, it's bounded by epsilon. Now, let's estimate the second term, x and r. Well, again, r, now it's larger than p0, which is larger than p1. And this means that x and r minus x, it's bounded by epsilon. So this quantity here, it's also bounded by epsilon. And therefore, for any n larger than np0, xn minus x, it's bounded by 2 epsilon. And that proves that indeed xn of omega converge to x of omega for all omega in A. Since A has probability 1, this means that xn converges to x almost surely, and this is exactly what we wanted to prove. Now let's go back to the theorem, to the main theorem of this lecture. And I will state it again for you to remember. So we have a family x1, x2 of independent random variables. And I define Sn as the partial sum. So the sum from 1 to n of xj. And what I claim is that, well, assume that this sequence converges in distribution. So let me take f of Sn as the distribution function of the random variable Sn, and I'm assuming that fSn is converging in distribution to some f. Then, what I claim is that there exists a random variable s such that Sn is converging to s in probability, and the distribution function of fs is equal to the distribution function f. So that's the first claim, is that, well, if Sn is converging in distribution, then actually it converges in probability. And my second claim is that if Sn is converging to S in probability, then it converges to S almost surely. So convergence in distribution of sums, partial sums of independent random variables, entails the almost sure convergence. So this is a very strong statement. So the proof, so I'll start the proof of claim 1, and let me, in order to prove, I'll start the proof and then I'll divide the proof in many claims. So the first one is that, well, since fSn it's converging in distribution to f, we have seen that this means that the characteristic functions of Sn are converging to the characteristic function of some distribution. So let me represent by fxj of t the characteristic function of the random variable xj, and by fSn the characteristic function of the random variable Sn. Well, since Sn is given by the sum of independent random variables, we know that fSn, which is the sum of xj from j from 1 up to n of t, that this is equal to the product of j equal to 1 up to n of fxj of t. And I know that this is converging to some characteristic function phi of t as n goes to infinity. And this holds for all t in R. Now, phi of t is the characteristic function of a random variable. This means that phi of 0 is equal to 1, and that phi is continuous. Since phi of 0 is equal to 1 and phi of t is continuous, this means that there exists a t naught which is strictly positive, such that phi of t is different from 0 for all t smaller than t naught. Phi is continuous. Since it's equal to 1 at 0, we can find an interval around the origin for which phi of t is different from 1. So my claim, my first claim, is that, well, let's consider the characteristic function phi of Sn minus Sm. So Sn minus Sm, it's the sum from m plus 1 to n of the variables xj at t. And what I claim is that this converges to 1 for all t less or equal than t0. So t0 is this value, which we know it exists. And now my claim is that, well, phi Sn minus Sm at t converges to 1 for all these t's. So I rewrote claim 1. I'm saying that phi Sn minus mt is converging to 1 for all t less than t0. And what we know is that phi Sn of t converges to phi of t for all t, and that phi of t is different from 0 for all t less or equal than t0. And here, to be clear, what I mean is that I'm taking the limit as m and n are converging to plus infinity. So this means that if I fix an epsilon and I take this difference, well, I can find n0 such that if m and n are larger than n0, then this difference is bounded by epsilon. So I want now to prove this claim, and what I will use are these two facts, which we already proved. So fix t such that t is less than t0, and fix an epsilon positive. I want to estimate phi Sn minus Sm of t minus 1. And I want to show that if there exists n0 such that if n and m are larger than n0, then this difference is small. Well, since I know that fSn minus ft is converging, fSnt is converging to ft, I know that there exists n0 such that fsk of t minus phi of t, that this is bounded by epsilon if k is larger than n0. Now, in order to estimate this quantity, what I will do is I will multiply and divide this quantity by phi of t, and I can do that because phi of t is different from 0. So this is equal to 1 divided by phi of t, phi Sn minus Sm of t, phi of t minus phi of t. I can divide by phi of t because phi of t is different from 0. Now here I want to compare this phi of t with phi m of t. So I'm taking this n0, which is whose existence we already proved, and I'm taking n and m larger than this n0. And now I'm rewriting this expression as 1 over phi of t. Then here, as I said, I want to rewrite this expression as Sn minus Sm of t. I'm assuming that m is smaller than n, and because, well, we have here Sn minus Sm, so this is implicit. And here I'm writing this phi of t minus phi m of t, Sm of t, sorry. So here when I said m, it's phi of Sm. And then we have phi Sn minus Sm of t, phi Sm of t minus phi of t. Right, so I just took phi of t and I subtracted and I sum phi Sm of t. So this is the first term, and then I have a second term. Now, of course, this is bounded by the sum of the first absolute value plus the second absolute value. Now, here I can also write this product as a product of absolute values. So let me do that. And what I get is that I have here an absolute value and here an absolute value. Now, this is a characteristic function, so its absolute value is bounded by 1. On the other hand, phi of t minus f phi of Sm of t, this is bounded by epsilon because we chose m larger than n0. So the first term is bounded by epsilon divided by phi of t. And, well, the second term, you see that since the random variables are independent, if I take the product of phi Sn minus Sm with phi of Sm, this becomes phi Sn. So I have here phi of Sn minus phi of t. And again, this is bounded by epsilon because n is larger than n0. So I get a second epsilon divided by phi of t. And so we proved that if I take a t smaller than t0, this difference is bounded by 2 epsilon divided by the absolute value, the modulus of phi of t, provided n and m are larger than n0, and therefore, indeed, phi Sn minus Smt converge to 1 for all t smaller or equal than t0. So my second claim is that phi Sn minus Sm of t converge to 1 for all t. So we proved that for t smaller than t0. Now I claim that actually this happens for all t. And the proof of this claim is as follows. Well, assume that this is true for all t less or equal than a, then I claim it's true for all t less or equal than 2a. So if we can prove that, since it holds for t0, we can just enlarge this interval as we wish in order to show that this is true for all t. And well, the proof of this second claim, so this is my second claim, follows from the following estimate. Well, I claim, and I leave that as an exercise, and you'll see in the notes indications how to prove this inequality. I claim that if you take any characteristic function phi, if you take 1 minus the real part of phi at t, so that this is bounded by 4 times 1 minus the real value, the real part of phi at t over 2. Right, so, well, you can, the proof of this exercise is not very difficult, but you can find the indications in the notes on how to prove that. And I will use this, this inequality in order to prove my claim. So let me take, I want to prove that this limit holds for all t less than 2a. So let's take a t which is bounded by 2a. This means that t over 2 is bounded by a. And what we have is that one of real part of phi Sn minus Sm of t. Note that phi, the absolute value of phi, the modulus of phi, it's bounded by 1. So the real part of phi is less or equal than 1, and therefore this quantity here, it's positive. So this positive quantity, it's bounded above by 4 times 1 minus the real part of phi Sn minus Sm t divided by 2. Now t divided by 2, it's bounded by a. So by assumption, we know that, well, this is converging to 1. Phi Sn minus Sm of t divided by 2 is converging to 1. This means that the real part, it's also converging to 1. And therefore, 1 minus the real part, it's converging to 0. So this is converging to 0 as n and m are converging to plus infinity. And therefore, well, this quantity which is positive, it's also, and it's bounded by a quantity which is converging to 0. This means that 1 minus the real part of phi Sn minus Sm of t, it's converging to 0. Well, but since you know that the absolute value of phi Sn minus Sm is bounded by 1, if you know that the real part, so this means, well, let me go step by step. This means that the real part of Sn minus Sm of t, it's converging to 1, as n and m are converging to plus infinity. And since phi, the absolute value of phi, is bounded by 1, this means that phi Sn minus Sm of t, it's converging to 1. So we proved our claim. We took any t whose absolute value is bounded by 2a, and we proved that phi Sn minus Smt is converging to 1 as n and m are increasing to plus infinity. So this proves our second claim in the proof. So now my third claim is that Sn minus Sm is converging to 0 in probability as n and m are converging to plus infinity. What we proved so far is that phi, the characteristic function of Sn minus Sm of t, is converging to 1 for all t as n and m converge to plus infinity. So let me recall, what does that mean? That means that for all epsilon, the probability that Sn minus Sm is larger than epsilon, that this converge to 0 as n and m converge to plus infinity. Right, so that means that for all delta, I can find n 0 such that this probability is bounded by delta if n and m are larger than n 0. So in order to prove that, let me fix p, an integer larger or equal than n, and let me consider, so let me fix epsilon, and now let me fix p, and let me consider the supremum for all n larger than m, larger than p of this probability. So I'm taking the supremum. Well, I can find np and mp which almost attain this supremum. This is a sequence of numbers, real numbers between 0 and 1. So it has a supremum. Its supremum can be approached. So I can find np and mp, which are larger than, so np larger than mp, which is larger than p, such that this probability is bounded by the probability that Snp minus Smp larger than epsilon, and, well, let me add 1 over 2p. So if I fix an error 1 over 2p, I can find np and mp which satisfy that inequality. So these integers almost attain the supremum. Now let me define a sequence, Zp, which is Snp minus Smp. And what do we know about Zp? Well, we know that its characteristic function, fzp at t, which is phi snp minus smp at t, well, by assumption, this is converging to 1. By assumption, this is converging to 1 because, well, as p increased to plus infinity, np and mp increased to plus infinity due to this inequality. So this is converging to 1 for all t in R. Okay, because this is what we proved so far. But 1 is the characteristic function of the random variable which is concentrated at 0. So phi I'm representing by phi 0 the characteristic function of the random variable which is equal to 0 with probability 1. And since we have this convergence for all t, we have seen by the Levy continuity theorem that this means that Zp it's converging to 0 in distribution. And we also seen that if you are converging to a degenerate distribution, this means that you converge in probability. So we know that Zp converge to 0 in probability. Okay, so I will erase everything. I'll just keep this fact that we just proved, that Zp, where Zp is this random variable, converge to 0 in probability. So we define Zp as this difference, and we proved that it converged to 0 in probability. So since it converged to 0 in probability, this means that for all epsilon, and for epsilon given by this quantity, the probability that Zp is larger than epsilon converge to 0. So fix a delta positive. So there exists a p naught such that if p is larger than p naught, then this quantity it's bounded by delta. Now if n and m are larger than p naught, the probability that Sn minus Sm are, that this difference is larger than epsilon, it's less or equal than the supremum for all n and m larger than p naught, but this supremum it's bounded by the probability that Z p it's larger than epsilon plus 1 over p. And this quantity it's bounded by delta plus 1 over p. So if we chose p naught not only large enough for this to be happen, but such that 1 over p it's less or equal than delta, then this is bounded by 2 delta, and we just proved that indeed Sn minus Sm converge to 0 in probability. Well, we proved that Sn minus Sm converge to 0 in probability, and we can now apply Lemma 1 to show that there exists a random variable S such that Sn converge to S in probability. So claim 4 is just the Lemma 1 which we proved at the beginning of this lecture. And now last, so we already proved that there exists a random variable S such that Sn is converging to S in probability. So the last claim of this first part of the proof, or the proof of the first assertion of the theorem, is that the distribution function of this random variable fs it's equal to the distribution function of S. So remember, we started from a sequence Sn such that the distribution function of Sn it's converging to f in distribution, and now we obtained a sequence Sn which is converging in probability. Since Sn is converging in probability, it's converging to S in distribution, So this means that also Fsn it's converging to Fs in distribution. Well, and that proves that Fs is equal to F. If you want a more formal proof, what you know is that if you take a bounded continuous function, let's say h, defined on R, and you consider the expectation of h as n, well, since Sn is converging to S in probability and in distribution, this converge to the expectation of Hs. And I can write that as H d mu S. So mu S is the distribution measure of the random variable S. On the other hand, since Sn is converging by a hypothesis in distribution to F, this is converging to the integral of H d mu, where mu is the distribution measure associated to the distribution function F. And therefore, H d mu S is equal to H d mu for all bounded continuous function, and that proves that mu S is equal to mu, and therefore that the distribution functions are also equal. So that completes the first part of the first claim, the proof of the first claim of the theorem, so that if you have a sum, partial sums of independent random variable converging in distribution, then they actually converge in probability to some random variable S. So now let's turn to the second claim of the theorem. We have a sequence Sn converging in probability to S, where I remember you, Sn is the sum of independent random variables, and I claim that then Sn converge almost surely to S. And the proof will be based on the second lemma that we stated. So we know that Sn converge in probability to S. This means that this implies that Sn is Cauchy in probability, which means that for all epsilon positive, the probability that Sn minus Sm larger than epsilon converge to 0 as n and m converge to plus infinity. So that's clear. If Sn converge in probability, then Sn is Cauchy in probability. And what I claim is that we can prove by using Levy theorem a stronger statement. So that what I claim is that actually the probability that the maximum for k between m and n of sk minus sm larger than epsilon, that these converge to 0 as n and m converge to infinity. So what we will prove is this statement, and if we are able to prove this statement, I claim then the theorem is proved, because we have seen in Lemma 2 according to Lemma 2, then there exists a random variable, let's call it S prime, such that Sk converge to S prime almost surely. Right? So if we are able to prove this statement, then by the second lemma of the beginning of this lecture, we know that there exists S prime such that Sk converge to S prime almost surely. Now Sk converge to S prime almost surely, Sn converge to S in probability. This implies, and I leave it to you to check it, it's a very simple exercise, that S prime is equal to S almost surely, and therefore that Sk converge to S almost surely, as we claimed. So what we really need to prove is this statement, that the probability of this maximum converge to 0 as n and m converge to plus infinity. So I wrote what we have. We have that Sn is Cauchy in probability, and what we want to prove is that for all epsilon, this probability is converging to 0. Well, to show that it's converged to 0, what we need to prove is that for all delta, there exists an n0 such that if m and n, well, let's say that n larger than m larger than n0, so that there exists an n0 such that if n is larger than m larger than n0, then this quantity, it's bounded by, this probability, it's bounded by delta. So this is what we need to prove. And actually, well, we won't prove that it's bounded by delta, but we'll prove that it's bounded by delta 1 minus delta, but this is exactly the same. So if we prove that this is, for all delta, this is bounded by delta 1 minus delta, we can show that it's bounded by delta by changing the definition of delta. So let's prove this statement, and to prove this statement, so we fix an epsilon positive and a delta positive. It follows from this limit that there exists n0 such that the probability that Sn minus Sm larger than, I'll take epsilon over 2, that this is bounded by delta for all m, for all n larger than m larger or equal than n0. Since Sn is Cauchy in probability, this means that for all epsilon and delta, we can find n0 such that this probability is bounded by delta. Now, note, let me just write what this is. So this is a sum of xi from I going from m plus 1 up to n. And what I want to do is the following. You have here your n0, and I will fix q and p. So q will be larger than p, and both will be larger than n0. And I want to apply this result to n equal to q and m equal to k, where k will run from p plus 1 up to q. So q will be our n in this inequality, k will be equal to our m, and k will vary from p plus 1 up to q. So the range at which I want to apply this inequality is for p plus 1 less or equal than q, less or equal, than k, less or equal than q. So let's simply write down what we have here for k equal to m and q equal to n. So what we have is that the probability that the sum from k plus 1, or let me call it I, equal to k up to q of xi, that this is larger than epsilon over 2, and this is bounded by delta. And this is true for k running from q to p plus 1. Right, so here is p plus 1. P plus 1, well, since p, I'm taking here, remember, p larger than n0, so we have that this inequality, so actually I'm taking k equal to m plus 1 in this. I'm taking k equal to m plus 1, so this is telling me that this sum from k to q is that the probability that this is larger epsilon over 2 is equal to delta. So here k, this means that I'm taking this sum from q to q, the sum from q minus 1 to q, the sum from q minus 2 to q, up to the sum of p plus 1 to q. And for all these, I'm saying that this probability, it's larger, that the probability that this is larger than epsilon over 2, it's equal to delta. So this is exactly the hypothesis of the Levy inequality Levy Bound. Since the random variables are independent, we can apply the Levy Bound, and the Levy Bound will tell me that, well, since this is true for all k between p plus 1 and q, then the probability that the sum from p plus 1 up to j of xi, that this is larger than 2 times this quantity, which is epsilon, that this is bounded by delta 1 minus delta. And here now I have a maximum according to Levy. So I can take the probability of the maximum now for j running from p plus 1 less or equal than j less or equal than q. Or that's the same thing, p less than j less than q. So this is what Levy Theorem, which we proved in the previous lecture, tells us, that if this is true, then we can conclude that this is true for all j between p and q. And, well, but what is this? This quantity here is just Sj minus Sp. So what we proved is that the maximum for j between p and q of Sj minus Sp larger than epsilon, it's bounded by delta 1 minus delta. And this is exactly what we wanted to prove, right? We wanted to prove, you see that m is equal to p, n it's equal to q. We have the maximum of Sj minus Sp larger than epsilon, and as I said, well, we don't prove that this is bounded by delta, but by delta over 1 minus delta, but this is exactly the same thing. And so we proved what we wanted, and with that, we complete the proof of the second part of the main theorem of this lecture, and with that, I conclude this lecture.